Hi, welcome back. This is the review for test 3. This will cover chapter 9, so let me give you kind of the question pool from WebAssign. 9.1, questions like 5 to 10. 9.2, questions like 4 to 12. 9.3, questions like 1, 3, 4, 6, and 7. 9.4, we have questions like 1 to 11. 9.5, questions like 1 to 5. 9.6, questions like 1 to 6. 9.7, questions like 1 to 7. 9.8, questions like 1 to 13. I'm not putting 9.9 on the test. And then 9.10, I'm looking at 1 to 6, 10 to 12, and then questions like 15 to 17. Okay. Actually, okay, so that's the question pool. Let's get in there and start looking at some particulars. So 9.1, we were just studying sequences at that point, so not dealing with series, but we introduced the idea of a limit of sequences, which later became important for finding the sums of series. So what would happen in 9.1 is it would give you a term formula for the terms of a sequence, and then they would want you to find the limit of that sequence. Okay? And in general, we could use calculus, but then you had problems like number 7 where it didn't quite work because of that -1 to the n. We found in this case, if you were to just look at the even terms, like a sub 2n, they would all be positive. So you would have -1 to the 2, -1 to the 4, -1 to the 6. So essentially your formula for a sub 2n, more or less, is n all over n plus 9. I mean, technically it's 2n all over 2n plus 9, but the limit will just be equal to 1. So the limit here of the evens, as n goes to infinity here, is basically the limit of 2n all over 2n plus 9. And of course, if you just circle the high degree terms and take the limit of that, you would get 1. Okay. Then we shifted our attention to the odd terms and noted in this case, they'll always be negative because the -1 is going to be raised to an odd exponent. So you'll have a negative there. And then essentially the sequence just works like the n over n plus 9. Technically, you have to put the 2n plus 1 in here, but it'll have the same sort of behavior as the original terms of the series. It'll go to -1. So in the bottom, instead of n, you have 2n plus 1, then plus 9. Simplifying a little bit, -2n minus 1 all over 2n plus 10. And then taking the limit of the odds as n goes to infinity, we have the limit of -2n minus 1 all over 2n plus 10. Circling the high degree terms, you see you just have the limit of -2n over 2n, which is just -1, and then the limit of a constant is the constant. So you just get -1 in this case. So the deal is, if the limit of the even terms is different than the limit of the odd terms, there's no way for the sequence to converge. Okay, it will never ever get super duper close to just one particular value. So you would say the limit of the evens does not equal the limit of the odds, and then you can conclude the sequence diverges. Okay. The limit does not exist, and then the sequence diverges. Let me write that so you can see it a little better. Diverges. Okay. Okay, so that one's a bit tricky. Other sequences were a little tamer, but we may have introduced factorial notation. So if you didn't know factorial notation, something like this would probably trip you up. Okay, so in particular, I think this was n minus 2 actually. So first you kind of have to simplify the thing, and then you could take the limit of it. So to simplify the factorials, you can write it out brute force and then remove common factors, or you could use the recursive definition where you're just peeling terms off of the factorial. And it's because things like 5 factorial are really equal to 5 times 4 factorial. And then you could peel off the 4, so you get 5 times 4 times the 3 factorial. Okay, so you could keep doing that. And the denominator, it's best to do the peeling there. So in the denominator you have n factorial, but you could write that as n times n minus 1 factorial. And then you could write n minus 1 factorial as n minus 1 times n minus 2 factorial. And then you see automatically you have this nice cancellation, and you're left with the expression 1 all over n times n minus 1. So then we'll get the limit of that thing, 1 all over n times n minus 1. Oops, let me erase that so it looks a little nicer. And that limit will be 0. Okay. Make sure you read the directions. The directions I get are directly from WebAssign. So if you go and look at number 7 and number 9 in WebAssign, it says to find the limit and determine whether a thing converges or diverges. In this case, the limit is 0, and then of course if it just goes to some number like that, it will say it converges. Okay, but these things were just sequences. We had not really gotten to the series yet. Sequences become a way of studying these infinite series that we see in introduced in section 9.2. So moving on to section 9.2 then, we get a taste of our first types of series, the geometric and then the telescoping. So first, the geometric, number 7, wants you to find the sum, if possible, of the geometric series. It's given in this kind of written out form. So 49 minus 7 plus 1 minus 1/7 plus ... The formula for the geometric series, which you should have memorized, is the sum of a times r to the n from n equals 0 to infinity, and that equals a all over 1 minus r when the absolute value of r is less than 1. The a value is just basically the first term you see in the series. So for us in the problem 7, it's 49. The r value is the ratio of 2 consecutive terms, with the second term going in the numerator. So here we have negative 7 all over 49. Reducing, that will be negative 1/7. Okay, so our r value, in particular the absolute value of the r value, is less than 1. So we can go ahead and add this thing up using our formula. So the sum of this thing, which we can write in summation notation as 49 times negative 1/7 to the n. And then we could use our formula a over 1 minus r to add it up. So you'd have 49 for a all over 1 minus r. Be a little careful, r is negative here. That'll equal 49 all over 7/7 plus 1/7 is 8/7. And then multiplying by a reciprocal, you'll get 343 all over 8 for your sum. Okay, so you should be able to write things in summation notation, so converting that sum into this thing here I'm putting in the box, and then you should be able to add them up and using the a over 1 minus r. But additionally, you need to have this thing memorized. Okay. Let's look at one of the partial fraction problems, or the telescoping problems. So the way this one is written, it doesn't quite look like a telescoping, but it is, right? And on the test, I will tell you in particular which test I want you to use. So I'll say find the sum of the telescoping series, and you'll have to do this process with partial fractions. Okay. So make sure you read the directions. Anyways, to rewrite this thing, I'm going to need the partial fraction decomposition. So you have to factor the denominator. This looks like it'll be 3n and 3n, and then plus and minus, and then I think we want a 2 here and a 1 here. Okay, so I'll have a all over 3n plus 2 plus b all over 3n minus 1. I think I want to reverse that and put them in the other order. Sorry about that. So I'm going to put the 3n minus 1 first and then the 3n plus 2 second. It's just so the second term is negative and the cancellation will work a little easier. Okay, so first multiply through to get rid of all the fractions. So you're multiplying by this denominator, 3n minus 1 times 3n plus 2 on both sides. Okay, so on the left there, everything in the denominator cancels. You get 8. On the right, on the first distribution, the 3n minus 1s will cancel. You'll get a times 3n plus 2. In the second distribution, the 3n plus 2s will cancel, and you'll just get b times 3n minus 1. Okay, then I'm going to do the substitution method. So let n equal negative 2/3. So I'll have 8 equals a times 0 plus b times 3 times negative 2/3 is negative 2 minus 1 is negative 3. So b will be negative 8/3. And then try n equals 1/3. So you'll have 8 equals a times 1/3 plus 1/3 times 3 plus 2. So 1/3 times 3 is 1 plus 2 is 3. So a is 8/3. Okay, I'm going to go ahead then and rewrite this infinite sum as a limit. So we'll have the limit as, and I need another variable, k goes to infinity of the sum from n equals 1 to k. All right, so what you're getting there is a formula for the kth partial sum, and then if you take the limit of the k partial sum, it's going to give you the actual value of the sum. Okay, so rewriting then the 8 over 9n squared plus 3n minus 2, you'll have a, which is 8/3, all over 3n minus 1, minus b, which is negative 8/3, plus b, which is negative 8/3, all over 3n plus 2. Okay. And then you expand it and collapse it, right? So I have the limit as k goes to infinity. I'm going to want to write out the first 3 terms. So n equals 1, n equals 2, and then n equals 3. And you basically just write as many terms as you think you need, okay, for you to kind of identify the cancellations. Okay, so I usually just write out the first 3 and then the last 3. So the last 3, n equals k is the last one. That's the upper limit on the summation. And then n equals k minus 1. And then n equals k minus 2. Okay, and then I just plug those values into the formula that I got by doing the partial fractions. So I'll have 8/3 all over 3 minus 1 is 2, minus 8/3 all over 3 plus 2 is 5. I'll plug in 2, so I'll have 8/3 all over 6 minus 1 is 5, minus 8/3 all over 6 plus 2 is 8. Then I'll have 8/3 all over 9 minus 1 is 8, minus 8/3 all over 9 plus 2 is 11. Okay, then I'm going to start the last one and work backwards. So this last one is 8/3 all over 3k minus 1, minus 8/3 all over 3k plus 2. For k minus 1, you may want to actually write it out. So you're plugging in k minus 1 for n. So basically over here on the left, I'll write it in. 3 times k minus 1 minus 1, right? So it would be 3k minus 3 minus 1, which is, for the first guy, 8/3 all over 3k minus 4, minus 8/3 all over, and then you have 3 times k minus 1 plus 2, which is 3k minus 3 plus 2, which is going to be 3k minus 1. and then do the k minus 2's. So you'd have 3 times k minus 2 minus 1, which is 3k minus 6 minus 1, which is 3k minus 7, the 8/3. And then this will be 8/3 all over 3k minus 4. You can figure that out, or you could just see the pattern after a while, right? So if you do your cancellations, you see that this second guy cancels with the first guy in the next pair, right? So this guy will cancel with this guy will cancel with this guy that we don't see. The second guy here will cancel with this guy, and this guy cancels with this guy cancels with this guy, and then you're just left with 2 terms. Typically this is what happens, but sometimes you'll skip terms, so you need to look for the pattern. You can't just always say, ooh, it's the first and the last term. Okay, you need to write it out and figure out what exactly is the pattern, what's going on. Anyways, the last bit here, you need to take the limit of the surviving members. The second term here is going to go to 0 because the denominator is going to go to infinity. And then the first term is just a constant, so the limit of a constant is a constant. So you're going to get 8/3 over 2, which is 8/3 times 1/2, which is 4/3. Okay. So those can be kind of long, a little bit tricky there when you expand it, but that's kind of just the way they go. All right. So after the geometric series and the partial fraction, the telescoping guys, we introduced the integral test, which basically said if you take the integral of the terms of a series and it's convergent, then the series is convergent. Okay, so number 4, they present a series as infinite sum, and then kind of expect you to get the formula from that sum. Okay. The denominator there is some sort of arithmetic sequence, 4, 6, 8, 10, blah, blah, blah. You can use your formula to get to this a sub n equals a sub 1 plus n minus 1 times the difference formula if you need that. But you could probably just guess at it. Anyways, this will be 4 plus n minus 1 times 2, which is 4 plus 2n minus 2, which is 2n plus 2 for the denominator. Okay. Anyways, that will be our series, and we want to, well, in the directions, I'll let you assume it's continuous on the appropriate interval. So you're considering now the function, if I can get my pen to work here, it just does not want to work. I'll have to pause the video. Okay, so we're considering then the function f of x equals 1 all over 2x plus 2 on the interval from 1 to infinity, where the 1 to infinity is based off the summation. Okay, and generally you need to show it's continuous and positive, but on the test I'll let you assume that. So I'll say assume it's continuous, assume it's positive, and just show that it's decreasing. Okay, so for the decreasing part, the way you would do that is via a derivative, and then just mention that the derivative is negative, less than 0. So let's get the derivative, rewriting f of x so I can do a power rule and then a chain rule. So f prime of x is going to be negative 2x plus 2 to the negative 2 times 2, which will be negative 2 all over 2x plus 2 squared. That thing on the interval from 1 to infinity will definitely be less than 0. Okay, so you need to get the derivative, mention that it's less than 0, and then you can continue on with the integral test. Okay, so the integral test, what we're doing is taking an improper integral, and on the limits on the integral will be from the indices on the summation. So the lower index starts at 1 and then it goes up to infinity, and then we have 1 all over 2x plus 2 dx. Okay. We do our improper methods from 8.8, so we change this into a limit as b goes to infinity of the integral from 1 to b. We're probably going to need a u sub, so I'll let you could factor out, but let's do a u sub for 2x plus 2. So du will be 2 dx, and then dx will be du over 2. Okay. So I'll have then the limit of the integral of 1 all over u times du over 2, which is equal to the limit of 1/2 times the integral of 1 over u du, and then that thing's just a natural log, so you have the limit of 1/2 times the natural log, the absolute value of u. Let's back sub everything, so I have the limit as b is going to infinity of 1/2 ln absolute value of 2x plus 2 from 1 to b, and then I'll have the limit as b goes to infinity of 1/2 ln absolute value 2b plus 2 minus 1/2 ln absolute value of 2 plus 2, which is 4. And then as b goes to infinity, that first term is going to go to infinity. So it'll be infinity minus some number L, which is just infinity, which implies both diverge. Okay, so hence the series is divergent by the integral test. Okay. After 9.3, we introduce the comparison tests in 9.4. So basically, if you have a series that looks familiar, you can do a comparison test. There's two types. First, the direct comparison. Okay, so the first thing you need to do is show me an inequality. So you have 3 to the n all over 2 to the n minus 1. You're going to compare it with something. Usually you could just pick this, so you just kind of kick off the -1 portion in the denominator, and you have 3 to the n over 2 to the n. In order to produce that expression, I added something to the denominator. It's basically 2 to the n minus 1 plus 1. If you add something to the denominator, that makes it smaller. Okay, so our inequality direction is greater than. Secondly, we have to make a statement about our newfound series. So let me rewrite 3 to the n over 2 to the n over as 3/2 to the n, and then note the series of 3/2 to the n is geometric, right? This is just, and you need to note what kind of series it is. Either it's geo or it's usually p series. So in this case, it's geometric. The r value is 3/2, and that's definitely the absolute value of that thing is greater than 1. So therefore, it's divergent. Okay. So in this case, you have something below that's divergent, and it's going to force the series kind of above it to also diverge. So hence, both series diverge. Okay. So it's not an automatic thing. You need to have the correct inequality for this to work. If the series you're comparing it with is below the original series but convergent, it won't really tell you anything. The series above it could be doing anything. If the series you're comparing it with is above the original series and divergent, you really can't do anything with it, because the thing below it could be one or the other. The only two that work is when you have a series below the original series that's divergent. That'll force the other series to be divergent, or the series is above the original series and that series is convergent. If the series above is convergent, it forces the series below it to be convergent. Okay. Okay, the other test then is a little less it takes a little less thought. Problem 10, or maybe it's 16. I can't read my writing. So I'll just say it's problem 10. This is the limit comparison test. So you have in problem 10 the sum from n equals 1 to infinity of 1 all over n to the fourth times n to the fourth plus 4. Okay, so first you're going to compose a new series, and usually you could just kind of, again, pluck off the non-constant terms and use that, right? So in this case, you could, look at it as 1 over n to the eighth, or if you'd rather, you can distribute, get 1 over n to the eighth plus 4n to the fourth, and so you're kind of looking at this portion for your series. So the series you're comparing it with, I'm going to do a limit comparison with the series 1 all over n to the eighth. Okay, and this time it's a p series, right? So it's a p series. P is equal to 8, and it's convergent. Okay. So then you form a limit with the ratio of the original formula for the terms of the series and this new formula that we've created. And take the reciprocal. If you want to, you could distribute in the denominator like I did above. And then it's, the limit of a ratio of polynomials, if it's infinity over infinity form, is just the limit of the leading terms. So you'll just have the limit of n to the eighth all over n to the eighth, which of course is just the limit of 1, which of course is just 1. For the limit comparison, your limit value needs to be greater than 0 and finite, which this one is. And then you could conclude they both have the same behavior, whatever that behavior is, be it convergent or divergent. In this case, both converge. So people always think, well, if I get a limit out, that means they both converge. But no, it's dependent on the series you're comparing it with. Okay, whatever that behavior is determines the behavior of both series. So, presuming that the limit is finite and greater than 0. Okay, let's move on to then 9.6, where we introduce the ratio and the root test. In particular, I care about the ratio test. The root test just isn't used as much. So here we go. I have the series 3 to the n all over n to the fifth from n equals 1 to infinity. And you should have the criteria for the ratio test memorized. If rho is less than 1, it's convergent. If rho is greater than 1 or equal to infinity, it's divergent. And then if rho is equal to 1, the test is inconclusive and you have to try something else. But anyways, here we go. Limit of the absolute value of a sub n plus 1, which is 3 to the n plus 1 over n plus 1 to the fifth, divided by, which is the same as multiplying by the reciprocal of a sub n, which is n to the fifth all over 3 to the n. 3 to the n plus 1 all over 3 to the n, that's just 3. You subtract the exponents. So that term there would have been 3 to the n plus 1 all over 3 to the n, but that's the same as 3 to the n plus 1 minus n, which is equal to 3. Okay, so that first part is just 3, and then we have n to the fifth all over n plus 1 to the fifth. You could rewrite that if you want as the limit of the absolute value of 3n to the fifth all over n plus 1 to the fifth. And then the limit of that thing is just the ratio of the high degree terms, and it may not be obvious, but the denominator high degree term is n to the fifth. If you were to sit there and FOIL that thing out 5 times, the leading term would be n to the fifth. Okay, and then the numerator, you have 3n to the fifth, so we're looking at the limit of the absolute value of 3n to the fifth all over n to the fifth, which is just equal to 3. Okay, 3 is greater than 1. That implies the series is divergent. Okay. From there, we started trying to connect infinite series to functions, and we began by doing approximations of functions with polynomials. So 9.7, number 3, there's two types. There's Maclaurin and then there's Taylor. They're essentially the same. It's just Maclaurin is centered at 0. Okay, so in problem 3, they asked for fourth degree Maclaurin polynomial approximation for sine of x. So first you do your columns of information. So I need to go up to the fourth derivative because I need degree 4. Whatever the n value is, that's how far you go in the derivatives. Then you need to evaluate all the derivatives at 0 because we're looking for Maclaurin. Okay, so here I go. I got sine, then cosine, then negative sine, then negative cosine, then back to sine. Okay, evaluating, I'll have 0, 1, 0, negative 1, 0. And then it's basically just copying and pasting into your formula for the Taylor or the Maclaurin polynomial. So P4 of x is basically blank plus blank x plus blank x squared over 2 factorial plus blank x cubed over 3 factorial plus blank x to the 4th over 4 factorial. And then you're just copying and pasting the 0, 1, 0, negative 1, 0. And then if you want to, you can simplify that. It's not necessary for me, but it'll be x minus x cubed over 3 factorial. Okay, okay, so that's a Maclaurin. Let's look at a Taylor series, or Taylor polynomial as well. So I have f of x equals 1 over x squared. I want a fourth degree polynomial again, and I want it centered at 2. Okay. All right, so again, I need 4 derivatives and evaluate all the derivatives now at 2. So f of x, rewrite it so you could do power rule. Prime of x negative 3 prime. It's going to be a 3 factorial. It's negative 4 triple prime. It's going to be negative 4 factorial x to the negative 5. And then the fourth derivative, 5 factorial x to the negative 6. Then evaluate them all at 2. Okay. So I'll have I'm not going to multiply anything out. I just like to leave it kind of as is. So negative 2 all over 2 cubed, and then we have 3 factorial all over 2 to the 4th, negative 4 factorial all over 2 to the 5th, and then 5 factorial all over 2 to the 6. Make that look like a 4. Okay, and then we could just dump it into our formula for piece 4 of x. Okay, so what is this thing? Box plus box x plus, whoops, and these cases, if you have a Taylor, you have to shift all the x's over by the center. So if the center is 2, you have to write x minus 2. If the center is negative 2, you'd have to write x minus negative 2 or x plus 2. Okay, so this, and then x minus 2 squared all over 2 factorial plus blank times x minus 2 cubed all over 3 factorial plus blank x minus 2 to the 4th all over 4 factorial, and then just copy and paste And you do, if you're on top of things, you do kind of see a nice little cancellation amongst the factorials. which could lead you to simplify and rewrite it as this. Because 3 factorial all over 2 factorial is the same as 3 times 2 factorial all over 2 factorial, which is just 3. Okay, so you'll have 3 times x minus 2 squared all over 2 to the 4th. And then minus this next one, 4 factorial over 3 factorial will be 4. X minus 2 cubed all over 2 to the 5th. And then 5 factorial over 4 factorial will just be 5. Minus 2 to the 4th all over 2 to the 6th. Okay? But either answer is fine. You don't necessarily have to simplify if you don't want to. But later in 910, it seems like you pretty much have to kind of have it in the simplified form for the summation notations. Okay. Okay. Anyways, let's move on to section 9.8. So 9.8 introduced the radius of convergence for these power series, and that basically just tells you, when they're useful. When can you use them for almost in place of the functions they represent. Okay, so number 7, we have the sum of 5x to the n all over 2n factorial. So we want to find out, where does this thing converge, right? So not only is it useful later than in 910 for knowing whether or not a series converges to the function, but also it's kind of like doing 9.2 to 9.6 again, except you're killing millions of birds with one stone, right? In 9.2 to 9.6, it was like working in arithmetic. Now it's kind of like we're working in algebra because we've introduced this variable x. Okay, but anyways, let's go ahead and find the interval of convergence. So there's 3 possibilities. It converges everywhere, it converges nowhere except the center, or it converges in some interval. And the interval one's the hardest because you have to check the endpoints. Okay, but anyways, let's take a look at this guy. So we want to use the ratio test, the limit of the absolute value of 5x to the n plus 1 all over 2 times n plus 1 factorial, divided by or multiplied by the reciprocal. Then we have 2n factorial, and this should be in parentheses like this, all over, so this should be like this, all over 5x to the n. Okay. If you were to simplify this portion by subtracting exponents, you would have 5x to the n plus 1 minus n, which would just be 5x. And then you have 2n factorial all over 2n plus 2 factorial. And then you could start, if you want to peel terms off the factorials to figure out what you're left with, that's usually the quickest way to do it. So 2n plus 2 factorial is 2n plus 2 times 2n plus 1 factorial. But 2n plus 1 factorial is 2n plus 1 times 2n factorial. So you could write it like that, and then you see the nice cancellation between the 2n factorials. And so you're left with the limit of the absolute value of basically just 5x all over 2n plus 2 times 2n plus 1. Okay, and that form is L over infinity, right? That 5x is just some sort of constant. If you would like to, you can factor it out completely and not have to worry about it, and just take the limit of the absolute value 1 over 2n plus 2 times 2n plus 1. Okay, so you'd end up with absolute value of 5x times 0, and anything times 0 is just 0. So the row value in this case is always going to be 0 no matter what x you pick. That value is always less than 1, which implies it's convergent everywhere. Converges for all x. On my test, I'll be asking for the interval of convergence. So the interval of convergence in this case is negative infinity to infinity. Everything. Okay. let's look at number 11. Number 11 is one of the ones where you have an interval and you have to check the endpoints. Okay, so this sum from 1 to infinity of -1 to the n plus 1 times x minus 2 to the n all over n times 2 to the n. So we begin again with the ratio test. We have rho equaling the limit of the absolute value of, you can disregard the -1 to the n plus 1. We'll have x minus 2 to the n plus 1 over n plus 1 times 2 to the n plus 1 times the reciprocal of a sub n, which will be n 2 to the n all over x minus 2 to the n. Okay, so we'll have the limit of, and again you can begin by simplifying this thing here. That will just give you x minus 2. So I have an x minus 2. Then you could simplify the 2 to the n all over 2 to the n plus 1. That'll just be 1/2. So x minus 2 over 2. And then you have this n all over n plus 1. Because the limit is always dependent on n, it says n goes to infinity, you could factor out anything that's not dependent on n. So you could factor out the x minus 2 over 2, but you have to keep the absolute values on it. The absolute value of x minus 2 over 2 is the same as the absolute value of x minus 2 over the absolute value of 2. The absolute value of 2 is just 2. Okay, so you have that, and then the limit of the absolute value of n over n plus 1. You don't really need the absolute value there, but I put it in anyways. Doesn't matter. And then the limit of n over n plus 1, again, you just take the ratio of the high degree terms. N over n is just 1. The limit of 1 is 1, so you get x minus 2 over 2. And then this thing has radius from, we have to have this thing less than 1, right? So if that thing is less than 1, this absolute value thing, that'll imply that x minus 2 over 2 is less than 1 but greater than -1, then you're solving for x. Okay, so you have -2 less than x minus 2 less than 2, and then you have x less than 4 greater than 0. Okay, so the radius here is just 2, half that interval. Okay, but I'll ask for the interval of convergence, and for that you need to go back then and check the endpoints. So starting with x equals 0 and putting it into the original series, I'll have the series -1 to the n plus 1 times 0 minus 2, which is minus 2 to the n, all over n times 2 to the n. And now I need to simplify this before I can really see what's going on. So I'll have the sum of -1 to the n plus 1. I can split the negative out of that -2 to the n, right? So it's -2, basically, long story short, -2 to the n is -1 times 2 to the n. And then we could go ahead and rewrite that as -1 to the n times 2 to the n. Okay, and that'll be all over n times 2 to the n. There's a nice little cancellation. Boom, boom. The -1s are like bases, so you can add the exponents. And you get -1 to the n plus 1 plus n, which is 2n plus 1, all over n. Then you could split up the -1 to the 2n plus 1 into -1 to the 2n times -1 to the 1. -1 to the 2n is -1 squared to the n, which is just positive 1. So you'll have just -1 over n when all is said and done. This thing then is the harmonic series times a constant, but it's basically a harmonic series. And we all know the harmonic series is divergent. Okay, so one endpoint down, one to go, right? So I'm going to go over here to x equals 4. I think the simplification would be a little bit easier this time. I have -1 to the n plus 1 times 4 minus 2 to the n. That will just be 2 to the n, all over n, 2 to the n. Yeah, and you see the 2 to the n's will just cancel, and you'll have the series -1 to the n plus 1 all over n. And so that's an alternating series, so we try the alternating series test. So first, take the limit of a sub n. That'll be 0. And then secondly, look at the, see if it's decreasing. And what I do is look at the ratio of a sub n plus 1 over a sub n and show that's less than 1. So n over n plus 1, you have something small over something bigger. That's definitely less than 1. So by the alternating series test, this thing is convergent. So hence, convergent. Okay, so at the end of the day, the interval of convergence, the IOC, is going to go from 0, which is divergent, all the way to 4, which is convergence. Okay, I'm not going to put 9.9 on the test. It's kind of the backdoor method for constructing power series representations for functions. Every once in a while, that kind of work is useful. If you can kind of see 1 over 1 minus x as a geometric series, that helps every once in a while. But for our purposes, 9.10 is kind of where it's at. And what we're doing here is basically constructing Maclaurin and Taylor series representations for functions. And I expect your answer in summation notation. Okay. I will tell you where to start your lower index on your sum. So in this case, I want you to start at n equals 1. Okay. All right. So first, what you want to do is kind of create your columns of derivatives and then evaluate them at the center. So this is a Taylor series this time. The center will be 1. And what I'm doing is just kind of populating enough of these so I can see the pattern. Whoops. So the derivative of x to the negative 1 is negative x to the negative 2. And then we have 2x to the negative 3. I usually just go down to about the 4th derivative, and that's usually enough for me to see what's going on. So we have a factorial type thing there. We have an alternating negative going on. And then we kind of have a factorial expression as well. Okay, so I'm going to go to my summation notation. I'm starting at n equals 1, going to infinity, and then I populate it with all the information I need. So normally your summation would look like this: fn of c all over n factorial times x minus c to the n. Okay, so I basically need a formula for the nth derivative evaluated at c, which is this sequence of values. Okay, and if you notice one thing, it's alternating. So I need some form of negative 1 either to the n or to the n plus 1. So if I put it to the n plus 1, the first one, and I'm probably going to have to start with this one. Okay, so the first one will be positive, and then the second one is negative, starting with the first derivative. Okay, so if n equals 1, I want that to be positive, so I got to put an n plus 1 here. Then there's a factorial, right? So when it's 2, it's basically 1 factorial. When it's 3, it's 2 factorial. When it's 4, when n is 4, it's 3 factorial. So it looks like it's always 1 less than n factorial. And then you just borrow the rest of this stuff from our generic form for these series, and the denominator has to be n factorial, and then you have to multiply by x minus c to the n, and our c value is 1. So I'll just put 1 there. Then simplify it, so n minus 1 over n factorial is just going to be 1 over n. So negative 1 to the n plus 1 all over n times x minus 1 to the n from n equals 1 to infinity. Okay. Okay, so that'll give you, so as usual, you know, I'll base a lot of the problems off of these guys here. I'll just change the numbers a bit. And then I'll probably put, you know, 3 or 4 kind of random problems from the question pool that I give you up here. Okay, so just to keep you on your toes, make sure you're doing your homework. But that's about it. That's the big and the small of it. Okay, so good luck on this test 3, and okay, I'll see you next time.